So topic 2.7 is about composition of functions. I'm not really sure if we've ever seen this sort of thing before, but the really basics of composition is evaluating functions with function notation, which I know we've done before. So if we're working with the function f of x, which is 2x minus 3, and I asked you to evaluate f of 5, what is it telling you to do? Plug in a 5. So we would say 2 times 5 minus 3. 2 times 5 is 10. 10 minus 3 is 7. So f of 5 is equal to 7. I changed nothing about what we've been doing since Algebra 1. Whatever is inside the parentheses, we plug into the function. Well, what if it's a letter C? We still plug it into the function, which means this would now read 2c minus 3. There's nothing to simplify there because 2c you can't actually multiply since c is still a variable. So we would stop here. What if it said 4a? f of 4a. That means I'm plugging in 4a anywhere there was an x in the original problem. Well, that one I have a little bit of simplification I can do because 2 times 4 is some math I can do. So 2 times 4 is 8a minus 3. So we've seen that we've plugged in a number, evaluated to a number. We've plugged in another letter, essentially switching the letters. We've plugged in a letter plus a coefficient, which meant we did have to do a little bit of simplification. What if we plug in a whole other function? This one's telling me to plug in 5x minus 1 into the original function itself. So this is going to look like this. We're going to say 2 times the stuff I'm plugging in minus 3. Well, this definitely has a little bit of simplification I can do because this is a whole distribution moment. 2 times 5 and 2 times negative 1. That's 10x minus 2 minus 3. Again, we simplify as needed, which is minus 2 minus 3. This actually simplifies to 10x minus 5. That is called evaluating functions. Whatever is plugged into the parentheses of f of x, that's what you're plugging into the function. Does that make sense? Okay. What if I make it a little bit more complicated? I'm going to let g of x be equal to 3x plus 1 and let the value g of 2 be equal to some number c. We're going to find out what g of c is. Whoa. So first things first, we're going to figure out what g of 2 is actually equal to. So if I do g of 2, just like above, that means I'm going to plug a 2 in for x everywhere there was an x. 3 times 2 is 6. 6 plus 1 is 7. So we know that g of 2 is equal to 7. Hooray. Here's the thing we also know, though. We know that g of 2 is equal to c. So what's the value of c? 7. We just found what g of 2 was. G of 2 is 7. That means that the placeholder c is actually the value 7. To answer the actual question here, it says find g of c. So what number should I actually plug in for g of c? Should plug in 7. Which means we're doing 3 times 7 plus 1. 3 times 7 is 21. 21 plus 1 is 22. So what happened there? What did I do when I did g of 2? I plugged in a 2. I got out a number. Bless you. What did I do with the number I got out from g of 2? I plugged it back in. So we're saying the output of one evaluation, the thing we got out, becomes the input of a different evaluation. When you take the output from one function and plug it in as the input of another function, you are using what is called composite functions. So this is our focus of today, these composite functions. They're like functions inside of functions because you're taking output values from something else and using it immediately and plugging it back in. There are two ways we can write composite functions. The first one is called, well, they're both read the same. It will look like this. We're not going to call that fog. Please never, ever say fog. This is not called fog. This is the notation for composite functions. The other way we could potentially write the same problem looks like this. We have an f on the outside and a g on the inside. The way we read this out loud is we pronounce this as this is the f of g of x. We're not calling it fog. It's f of g of x. So either way it's written, this way, f of g of x, or this way, f of g of x. Those are both ways that you can see composite functions. I prefer writing it like this because it helps me work the problem. Sorry, I guess I should point with my little pointer. I prefer writing it like this personally, but this is still same. And you will see them interchangeably used. One is not better than the other. I just personally prefer this one because I feel like it helps me remember what to do. But what happens is we have functions tucked inside of other functions. These have been the things we've been using since forever. You just didn't know they were called composite functions. Before we get into actually evaluating them, we got to talk about composing them or decomposing them. So functions given analytically can often be decomposed, which means uncomposed, into less complicated functions. When properly decomposed, the variable in one function should replace each instance of the function with which it was composed. So this is not necessarily a complicated function, h of x. It says square root of x plus 1. But this is actually a composed function. Do you see that we have like an outside function and an inside function? The square root is on the outside and a function x plus 1 is on the inside. That means we have composed the following. We have composed the fact that f of x is just the square root of x, and g of x is that linear function we tucked inside of it. Because you have an outside function and you have an inside function. So this function h of x in the problem is actually f of x with g of x tucked inside. F of g of x. We took the blue function, we put it inside the red function. Putting one function inside another is called composing. Taking one function out of another is called decomposing. So if that's the case, if we look at B, for the j of x function, what would be like the outside function? What's on the outside here? Here's what I see on the outside. I guess maybe it would be easier to say, what's on the inside? Do you see how x plus 1 is inside a set of parentheses? We have tucked it inside another function. So we know for sure that g of x is going to be this x plus 1. Again, my linear function. But I put it inside of what kind of function? What is the red stuff? It is parentheses, but if you have parentheses with the square on the outside, what is that called? A quadratic, I heard it. X squared. Now I took the parentheses away when I wrote this down because when you just have a simple x squared, you don't need the parentheses. But when you tuck stuff inside a function, you do need the parentheses. So j of x is created by taking the outside function f of x and putting the inside function x plus 1 inside of it. Again, we're still decomposing here. If we look at letter C, which is k of x equal to 1 over x squared minus 3x plus 1, I'll tell you right now the inside function is this. If that's the inside function, what has it been tucked into? 1 over x. That right there is my outside function. So our f of x, our outside function, is 1 over x. But in place of x, instead of x, we put the whole g of x function, which is the quadratic x squared minus 3x plus 1. So again, k of x is going to be equal to f of g of x. So identifying smaller functions inside larger functions actually helps us compose them or use them, which is kind of the point of today. If you look at part D, what kind of functions do you have? Let me rephrase. What's on the inside here?
3x minus 7.
3x minus 7. We have a linear function, 3x minus 7, and it is tucked inside what kind of function? What's this called? Absolute value. So my two functions that were composed together were the outside function, absolute value of x, and the inside function, 3x minus 7. So that r of x was created by an outside function of f of x and an inside function of g of x. So that's decomposing. That's taking an already composed function and saying, this is what we plugged in there. An important note for us, and I'm realizing that I don't know if I've done a good enough job explaining the different restrictions on domains for functions. There are only 3 functions with restrictions on their domains. This is not in your notes, but I need you to put it there because this is super important. We've already talked about one type of function with restrictions in their domain. We knew that when we did rational functions, what can the denominator not be equal to? 0. So there is a restriction on the domain or on the input values I can use for a reciprocal function or for a rational function. There are 2 more, one of which is the square root function. Think about square roots in general. What numbers can you not take the square root of? Negative, unless you make them imaginary. So if we're dealing with real numbers on a real number line for graphing, we know that x has to be from 0 to infinity because we can't take the square root of a negative number. So it's only the positive numbers, including 0. The other one is called a logarithmic function. We haven't studied this necessarily yet. We will get there. That's our next unit. Logarithms also have a restriction on their domain. Their domain is from 0 to infinity, but you can't include 0. These are the 3 functions in this class that do not have a domain of all real numbers. They need to be 3 things that we just know factually in our brain. One of them we've covered, the rational functions. Square roots we don't necessarily cover, but you talked about that in Algebra 2 and how you can't take the square root of a negative number. That should make sense to us. And then for logarithms, I will get you, that is our next topics in this unit, but we can only go from 0 to infinity, not including 0. So these are important notes for you. Any other type of function, you say the domain is all real numbers, period, you're done. These are the only 3 where that question requires any sort of thought. Okay? Now, when we are actually composing functions ourselves, we have to make sure that we potentially restrict the domain as necessary. The domain of a composite function is restricted to the input values of g, inside function. Look, we'll color code. So we have g on the inside. We're talking about g, for which the corresponding output value is in the domain of f, the outside function. AKA, this means that we need to find and use the domain of the inside function as well as the domain of the composed function, even if the inside function disappears, which is why we have to make sure that we know the domain of the stuff we're plugging into each other before we even get started. Because your domain may disappear and you may give me an unreasonable domain because you forgot about the inside function. So for example, example 3 says perform the composition and then state the domain. So we are trying to do, again, f of g of x. So f is my outside function. This is going to be my outside function. And g of x is going to be my inside function. Before we start composing anything, we need to talk domains. The domain of a quadratic is all real numbers. Should be an automatic response for us since Algebra 1. Plus, it's not on my list of 3 things. But a square root does have a restriction on its domain. We know its domain can only go from 0 inclusive to infinity. So we have bracket 0 to infinity. Yes, we agree those are the domains of those functions. Can't take the square root of a negative number, but you can square any particular number you have. Okay, so we start to compose this. We would say f of g of x based on evaluating functions means I'm going to take the function f of x and I'm going to plug in whatever the function g of x is, which for us is square root of x. Okay, I'm taking square root of x and I'm putting it inside x squared. When I put it inside x squared, it becomes square root of x squared, because f of x was x squared. Well, y'all, what's the square root of x squared? Yeah, that, like, they cancel each other out, right? So this becomes x. What kind of function is just plain x? Linear. The domain of a linear function is what? All real numbers. So if you just look at this and say, it's all real numbers, you're like, hooray, I'm done. No, we're not. What was the domain of the function we plugged inside? Zero to infinity. That domain takes over. From our answer, it looks like our domain should be from negative infinity to infinity, but in fact, we have to say, hold up, go back. Because we plugged in a square root function, we know that this domain is actually just from 0 to infinity. So we check the domain of the answer. It was all real numbers. We check the domain of the inside function. Whichever is more restrictive, you include. Which may mean you have to combine restrictions together. Kind of weird. Okay. Next problem. It says do f of g of x, but if you notice, I've switched which function is f and which function is g. So we're still doing f of g of x, but this time f of x is that square root of x, and g of x is x squared. Let's check domains. What's the domain of the red function? 0 to infinity, because you can't take the square root of a negative number. What's the domain of my blue function? Correct. All real numbers from negative infinity to infinity. Let's start composing. If still we are doing f of g of x, I'm still going to put f on the outside and g on the inside. Well, this time g is x squared. I take x squared and I put it inside the square root of x function because I'm tucking it inside there. So really this is square root of x squared. So again, what happens when you square root something that's squared? It cancels. What's the domain of this function?
0 to infinity.
I'm so glad you said that. So we're tempted to say 0 to infinity because the other one that was x was 0 to infinity. My question for you is, what's the domain of the inside function here? Negative infinity to infinity. So if my composed function, the black function, has a domain of all real numbers, and my inside function has a domain of all real numbers, my composed function keeps that domain from negative infinity to infinity. The difference between these two problems is what you plugged inside. Yes, we ended up with the same value at the end with the same function, but we had to restrict this domain because the inside function was square root. We did not have to restrict this one because the inside function was x squared. So you care about the inside function and the final composed function, which is weird concepts.
So only the inside one time.
The inside and the final, yes. So like if our final one ended up looking like 1 over x, we'd also need to restrict it based on that. But the trick with this is that the inside functions disappear sometimes, so you can't forget about those. So on the back side, we're going to start actually evaluating these composite functions. This is going to be a little bit easier than what we were doing on the front, because we're evaluating, for the most part, we should be getting a number answer. When we're evaluating a number in a composite function, we should get a output number answer. So when you're evaluating composite functions, we start on the inside. Oops, it's too big. We start on the inside. Ooh, let's focus. There we go. So if you are given, again, f of g of x, and they won't always be f and g, by the way, that's just the most common. And I'm going to keep using the same color scheme for insides and outsides. If you are asked to compose or evaluate a composed function, you evaluate g of x first. You get a number, 5, 8, whatever. You take that output and you take the answer from g of x, the output, and you plug it into f of x. That's what it's telling me to do when it says f of g of some number. So in example 2, it gives me the functions f and g. Just as a quick note, what kind of functions are f and g? Linear. Is there any restriction on the domain of linear functions? No, so we're good. We don't have to worry about that because it's all real numbers all the way around. But we're going to evaluate f of g of 3. Okay, here's how I want you to write this. If we're doing f of g of 3, that means we are doing f of g with a 3 plugged into it. I will zoom in here in a second. Notice, it is f on the outside, g on the inside, but inside of g is the number 3 that it asked me to find. Don't overthink it. What is 2 times 3 plus 1? 7. So really, this question is saying, all right, what about f of 7? Since g of 3 was 7, now we say, what about f of 7? Which means we do this. We do 3 times 7 minus 5. 3 times 7 is 21. 21 minus 5 means that this is equal to 16. So I took the number 3, I plugged it into G. I got 7. I took the output 7 and I plugged it into F. I got 16. Yes? I'm so glad you asked that. His question was, does the order matter? Look at the next question. It says G of F of 3. Should we get 16 as an answer? Let's try it. This time, the outside function is going to be blue because it says G on the outside. So I'm finding G of F of 3. Okay. Did I lose anybody right there? 3 times 3 is 9. 9 minus 5 is 4. So this is like saying G of 4. Make that the correct color. G of 4. Which means G of 4 would be 2 times 4 plus 1. 2 times 4 is 8. 8 plus 1 is 9. So to answer your question, does the order in which I tell you to compose them matter? Yes. You will not get the same outputs and inputs for every single time you compose a function. I'm going to let you guys try part C. Now I want to bring something to your attention about part C. How would you say that out loud, by the way? Of 4, yes. It's weird. It feels really weird coming out of the mouth like that. It is f of 4, which means your inside function is which one? And your outside function is which one? Okay, let's try it. I want you to go. I'm going to start working it as you're working with your team, so just don't look up until you're ready. Okay, how do we do on this? Did we also get 16? So notice, again, you plug in one input, you get that output, and it immediately becomes an input. So one output's doing two jobs. It becomes an output, then it immediately gets plugged back in as an input. That's composing a function. So make sure we notice, again, that composition is not commutative, which means order matters. If I ask you to do f of g of x, don't do g of f of x. The order completely matters. You start on the inside or on the right. Okay? Using the equations from above, so we're still using the f and g from the problem right above this, we're going to actually compose them and write expressions. So notice these questions don't have a number tucked in for x. We're just going to rewrite a new question like we did on the front side. Again, we're checking on the domains. We already said this before, though. We said that the domain of both of them is all real numbers. So we don't really have any new restrictions that will disappear from our domain here. It's always good to keep that in mind, though. If we're doing f of g of x, we are doing f of, and then my g of x function, which was 2x plus 1. That's what I'm plugging into the f function. So just like we did at the beginning of class, we're going to take that blue function and plug it into the red one, which means this would be 3 times 2x plus 1 minus 5. We've taken g of x, we've plugged it into f of x. This is a little bit of a distribution moment. So we have 6x plus 3 minus 5. Then we combine like terms. This is actually 6x minus 2. To list the domain, again, we remember that any linear function has a domain of all real numbers. We plugged in a linear function, which means its domain is still all real numbers from infinity to infinity. Negative infinity to infinity. It's always a good idea to check the reasonableness of your domain for the function you're using. A lot of times it doesn't really change, but it's always good to keep in mind if yours has a restriction, that restriction has to stay. Okay, this time it's your turn. Notice, again, that I switched the order on you. Part B is not f of g of x. How would you say part B? Yes, all of that mumbling I think was correct. G of f of x. Y'all's turn. Y'all give it a shot. All right, let's see how we did on this. To evaluate g of f of x, again, following the color scheme I have, this is going to be g of 3x plus minus 5, which means I'm plugging that red function into the blue one. This would be 2 times 3x minus 5 plus 1. We distribute for a moment. We would end up with 6x minus 10 plus 1, which simplifies to 6x minus 9. And again, the domain, because that's a linear function and we plugged in a linear function, is still from negative infinity to infinity. Check, done. All right, what if I give you more than 2 functions to deal with at a time? This time, I'm giving you 4 functions at a time. We're going to have h of x. What kind of function is h of x? So what's its domain? All real numbers. Then you have k of x. What kind of function is k of x? What is the domain of a quadratic? All real numbers. What kind of function is p of x? What's the big thing you see there? Square root. It is a square root function, which means that we know you can't take the square root of a negative number. So we have to do a little bit of work here to figure out what the domain is. Normally we just say from 0 to infinity inclusive, but if I plugged 0 in there, it would still be 1. I'm still allowed to take the square root of 1. So I have to figure out what happens if this would be equal to 1. Not 1, sorry, 0. Okay, subtract 1 from both sides, divide by 3. That means the very last number that I can take and plug into this function is negative 1 over 3. Because that's the thing that would make the inside 0. Anything less than that is going to make my square root negative, and we can't have that. So our domain here is from negative 1/3 to infinity instead of from 0 to infinity. Because typically 0 is the last number you can take the square root of. But for this function, because we have extra stuff on the inside there, it's already a composed function, by the way, we have to change our domain to adjust for that. What kind of function, though, is m? Ones that has a slope, so it's called a linear. Linear functions have a domain of all real numbers. So we only have one here, the green one, that has a restriction. When we use the green one, especially if we're using it to write an equation, we have to include that domain because it's not all real numbers anymore. First question, how would you say part A out loud? K of h of 2. Okay, if I follow my color scheme, that means I'm doing K of h of 2. So that means I'm plugging a 2 into the red function, and whatever I get out of that, I plug into the blue function. 2 times 2 is 4. 4 minus 3 is 1. Should be red. Which means I'm plugging a 1 into K. Well, K is a quadratic, which means there's two places I'm plugging in the number 1. I'm plugging it in where it's squared. Use the right colors. And I'm plugging it in here next to the 4. 1000% you need to use parentheses on this. We're not strong enough in our noticing of negatives to not use parentheses when we do this. So even though it's a simple 1 and you're like, parentheses are extra, put them. Put them. 1 squared is 1, 4 times 1 is 4, and 5 is a constant by itself, which means this evaluates to 10. How would you pronounce part B? Ooh, I'm so glad you said that. Did y'all hear what she said? This is not a time symbol. Honestly, please, I was going to make that mistake for me. This is not a time symbol. Do you see how it's like hollow? That's the composition symbol. So another way to write this is, color's H, is H of M of X. Sorry, -1. That's what that means. So the little dot right there doesn't mean multiply. The multiply dot is a filled in little dot, which is also why we don't really use it anymore, because that's just confusing. You can stick two things next to each other and it means you multiply. This symbol means compose. I'm going to leave you here. I want you to do H of M of -1. I'm going to go ahead and start working this as you're working with your team. How do we do on that one? Do we get it? Fabulous. All right, cool. Easy peasy. Evaluating on a number? Cake. What if I ask you to do part C? Let's try this again. How do you say part C out loud? K of P of X. Now again, I prefer writing it where one function is actually tucked inside the other. That's my preference as a mathematician, but this is absolutely fine. Again, because it's my preference, I'm actually going to rewrite this in the other form. For this other form, we would have K on the outside and P on the inside. Now notice we're not plugging in a value for this one. It doesn't have a number on top of X, which means we're just writing a new equation. If there's a number plugged in for X, that's when you should give me a number answer. But if there's an X plugged in, you're giving me an equation answer. Our spidey senses should also be going off because we just used the P of X function. We said that one has a restriction on its domain, so we got to keep that in mind as we're working. But if we do K of P of X, since there's no number to plug into P of X, I'm going to go ahead and plug P of X into K of X. Oof, okay, so I use parentheses and I'm going to square it, but inside that parentheses should be square root of 3x plus 1. And then I'm going to add, wrong color, I'm going to add 4 times that value again, which is square root of 3x plus 1. And then I'm going to add 5. It's complicated, But all we've done so far is take p of x, the green function, and put it inside the blue function. Do we agree? I put it everywhere an x was. Changed nothing else. Now we get to simplify. What happens when you square something that's square rooted? They cancel out. So this is going to become just plain 3x plus 1. Can you multiply a 4 into this square root? No, square root is protecting it, kind of like parentheses with a square. But what you can do is just place that little 4 in front of the square root, not as an index, but as a big 4. Make sure it looks bigger than the actual index. If you make that a tiny little 4th root, I'm going to read it as a 4th root. This is 4 times the square root. And then the plus 5 gets dropped down. Is there anything else I can simplify here? Yeah. The 5 and the 1. Classic little constants we can add together. The order I'm going to write this, not that it's the only correct order to write this function, is 3x plus 6 plus 4 times 3x plus 1. Some textbooks put the radical first. I prefer to put the radical last. It's not incorrect as long as the signs are all correct. However, this one has a restriction on its domain because we used the square root function. The blue function had a domain of all real numbers, but the green function had a domain of from -1/3 to infinity, which means we have to abide by that domain because it's still in the function. Number 1, it was my tucked in function, and number 2, that square root, I still see it. So it's still a part of my domain.
You can solve it in
You could, but it would just get, it wouldn't simplify to anything because we're not like solving it. So this would be as simplified as a question would want. Correct, yes. For lack of a better answer at this point, when it matches the key or it looks like an answer choice. If you're doing something and making it more complicated, you're not simplifying anymore. Because to fix this in any sort of way, I'd have to square everything and it would make it way more complicated. So we're just going to leave it like this. Unless it doesn't look like an answer choice, in which case, keep going. That's a good question. Oops, I didn't pause this. Whatever you want. Okay, on these problems, this time, I still gave you 4 functions. We have the function f. We have the function g. We have the piecewise function h. And we have a verbal description of the function k. So we have a graph. We have a table of selected values. We know nothing else about the g of x function except for these values. We have a piecewise function. Don't panic, we know how to handle that. And we have a verbal description of k of x. I would prefer that verbal description be written as an equation. So why don't we write this as an equation using what we know about transformations? It says k of x is a quadratic function with a horizontal translation of 2 followed by a vertical translation of -3. What does k of x actually look like if I were to write it out? How do you put a horizontal translation in a quadratic? Let me ask this a different way. Is horizontal translations inside or outside? Inside. Oh, so like today when we were tucking things inside a function, we're still going to have an inside transformation. Compositions are transformations. What? Horizontal transformations at least. And then we're going to have a vertical translation of -3. Where do I put that -3? At the outside, because we're subtracting every output by 3 to vertically translate it. So you could continue to read the verbal description, but I find it easier, again, to look at an equation. So now I have a graph, I have a table, I have a piecewise function, and I have a quadratic function. Our job is to answer all of the questions on this page with these 4 functions. They amp up in difficulty. The first one, actually the first 2 we're going to do together, and then we're going to play a game with the rest of them. But this first one says f of g of 3. Fabulous. What function is on the inside? G of 3. All right. So we say, okay, first, before I do anything with f, I have to evaluate g of 3. Everybody look at the g table. What is g of 3?
3.
I'm so glad there's like an awkward silence happening. Is there a 3 on that table? For x? For input values? The only input values I know about g of x are -4, -1, 2, 5, and 7. Is there any information about g of 3? No. So really, it's like this. Huh? You want me to plug in what? I don't even know what g of 3 is. Since g of 3 is not defined, we would answer this question with either not defined or undefined. Because based on the information we have, we are not going to extrapolate data today. Based on the information we have, we can't answer this question.
But you could.
If we knew what kind of function g of x was, and it allowed us to extrapolate data and create a regression for it, I mean, yeah, we're not doing that today. We don't even know what kind of function that is. Let's do the second one together. This one says what? How do you pronounce that? H of f of 8. Again, I prefer writing it in the other way because I think it tells me what to plug in where. So h of f of 8 looks like this. This is h of f of 8, based on the color scheme I used at the top of my paper. So this time, we go to look at f of 8. Remember, when you're reading a table, the 8 is here. What's the output of this function at 8? -1. So we go to read the table, or sorry, what's that called? Graph. Wow, I forgot the word graph. Happy Monday, everybody. So this is asking me h of -1. Okay, so we look at the h function. If I want to plug in a -1, am I using the first part of the piecewise, the second part of the piecewise, or the third part of the piecewise? Is -1 less than 1, equal to 1, or greater than 1? The first one, because -1 is less than 1. So, okay, that means I'm evaluating the absolute value of -7 plus 3 times -1. Well, 3 times -1 is -3. -7 plus -3 is -10. So what's the absolute value of -10? 10. So h of f of 8 is 10. Do you see how you're jumping from function to function? Inputs become outputs, and outputs become inputs. Why did we choose the absolute value? In the piecewise function, we have to decide which of those three we're using. And since the input value was -1, -1 is less than 1, right? That means this is the rule that takes over. If the number we were plugging in was 5, 5 is greater than 1, we would choose this one. Okay, if we don't remember how to play grudge, I'll show you in a second, but you are going to finish these notes with your team. Every time you think you have one done, you get to attack another team. I'll go over the grudge rules in a second. When you run out of problems on this one, like when you get through I, if you get through I, you'll probably get through I, you can start working from number 1 through the end of your homework assignment. So you're adding extra problems to your grudge game as we go. I will fill out the rest of the notes for myself and put them on the one that I upload online, but for right now, we're going to be done with me talking. Yes? Okay, I think we got it.